Welcome to topic 3.3.
In this topic, you will learn about the different kind of controls in the chilled water plant, as well as how are we going to determine when to start a new chillers, when to start the next chillers, when the load is changing. So that is what we usually call the chiller sequencing or chiller staging. For controls, if you are familiar with the control loops, usually there will be an input and there will be a respective output. And what happens is usually the output, right, it will control certain parameters. Certain parameters will be affected, and the parameters that's affected will, in terms, right, cause your input to change. Okay, and how do we know what kind of output to have? It depends on your set point. So these are the three terms that must be there for a closed loop control. So let me give you an example. For example, let's say the input, right, is the water flow, chilled water flow. Okay, let's say the input is a chilled water flow. So what do? You will use a sensor. Okay, you will use a flow meter, which is a sensor, to determine what is the current flow meter reading. For example, let's say the water flow now is 40 liters per second. And it will compare this value with your set point. And so let's say your set point is 45 liters per second. So what happened? That means you are not providing enough flow compared to the set point. This is your desired flow, but the current reading is only 40 liters per second. So what do? That is when you will need to ask the controller. There must be a brain somewhere. There must be a controller, which in the building aspect is always the BMS. The BMS consists of a controller that will tell that will compare these readings. Okay. So what you need to do now is to control a certain output such that your flow will increase. So we know that the flow is actually affected by the VSD, okay, the VSD of the pump. So VSD is the variable speed drive of the pump. So it will tell the pump to move faster, to increase the speed of the pump. So when it increases the speed of the pump, so here the VSD will ramp up. Okay, the VSD of the pump will ramp up. So when the VSD now is working harder, the pump is working harder, your flow will start to increase, maybe to 41, 42, until it is able to hit the set point. Then the speed of the pump will stay at that value. So this is a very typical kind of control loop, okay, that you can find all over the buildings. Okay, so this is one of the example in the chiller plant itself. For air side, in the air handling systems, there are various kind of controls as well. The temperature control, your static pressure control, etc. But over here, we will only look at the water side, okay, of water side controls. So over here, again, we are using a BMS schematic to illustrate my points. So you can see there are many readings here. Okay, a lot of values that is shown here. So there are a lot of sensors, there are a lot of temperature sensors, there are also a lot of actuators. Actuators is the one that control the valve opening. Okay, control the valve opening. So over here, you can identify different kind of sensors, like your flow meter, your temperature sensor, your pressure sensor in terms of PSI, okay, etc. So how does control in the chiller plant works? There are three basic configurations of chiller water piping in a chiller plant. So these are the trees. There are constant primary flow, constant primary variable secondary flow, and variable primary flow. Okay, so what's the difference between these three? First, let's look at constant primary flow, which is the most so-called primitive way of controlling the water flow rate in the chiller plant. So what we have is a pump that is attached in front of a chiller. So let's say you have 3 chillers, you will have 3 pumps. Okay, So whenever you start a chiller, for example, if your chiller 1 is being command start, your pump 1 will also start to kick in. Okay, will also go into operation. So one pump is tied to one chiller. Okay, and it will only be going at a constant speed. Okay, so you are not able to modulate the flow. You are not able to modulate the speed of the pump. Okay, so the advantage of using this kind of setup is the control is very basic. Okay, it's just either start or stop. There's no playing around with the flow rate and things like that. Okay, so but of course there's a lot of disadvantages, such as it's very inflexible. Let's say your cooling load is always changing, then you are not able to change the flow rate to meet the changing cooling load. Okay, so nowadays it's not very common to find constant primary flow anymore. Okay, only for those kind of buildings, maybe a small building, a small spaces that you want to cool down. Okay, then you may use this constant primary flow, and only when if the load doesn't change, maybe throughout the day, it's very standard, it's always at a certain load. Okay, and after that you switch it off. Okay, this is more common, and it's very common for large buildings. This is called constant primary, but you have secondary pumps. So the purpose of the secondary pump is to supply chilled water to various parts of the buildings. Okay, and for places with multiple buildings that share a single chiller plant, for example in a school, you may have 5 blocks. But all the 5 blocks, right, they share the same chiller plant at one of the block. Okay, so what happens is, all the 5 blocks, right, they may have 5 different secondary pumps that will supply water to the individual block itself. Okay, so this is better because when the cooling load change, your secondary flow will be adjusted accordingly because it's a variable secondary flow system. Okay, you have a VSD installed at that pump. Okay, so but this is more common for large building, large tonnage, okay, or multiple buildings kind of setup. And the last one, variable primary flow, this is getting more and more common because it's very energy efficient. Okay, but the control may be very complex because you are actually adjusting the flow that is going into a chiller. And as we know, chiller, right, okay, there's a minimum flow rate that must be supplied. Okay, if the flow rate is too low, your chiller may trip. Okay, it's very bad for your chiller. So although it's varying, the flow may change, okay, but there must be a lower limit. It must be bounded by a certain amount of flow. Okay, and this kind of setup is getting very common nowadays, okay, in new buildings. So what are some of the controls that we can apply, let's say for a chiller plant? Okay, so let's consider this. Okay, let's consider this a constant primary variable secondary piping configuration. Okay, what if the load changes throughout the day? So let's refer to this schematic, okay, of what you have on slide 21. So this is the setup. Okay, you imagine the load over here. Okay, the load over here, right, is your AHU. Okay, all these are your AHU and FCU. So let's say in the evening time, all your AHU start to all the load, okay, the cooling load in the space start to drop because people start to go home, the sun start to set, and your room start to get cooler. Okay, so if your load is dropping, the first thing that will happen is the control valve over here will start to close. Okay, so your AHU chilled water valve will throttle close. That is the meaning of this. Okay, if your cooling load is low, your chilled water valve will start to close because you don't have to supply so much chilled water to the AHU anymore. Okay, so what will happen if this happens? If your valve all start to close, right, okay, the differential pressure sensor that is attached to the supply and return line, okay, this is your supply pipeline, this is your return pipeline. Okay, so let's say you have a DP sensor installed to measure the difference in pressure. Okay, the difference in pressure will start to increase. Okay, when your valve start to close, right, okay, there's so-called more obstruction. your differential pressure will increase. So your DP sensor will increase above the set point. Okay, so there must be some corrective action. Just like the previous example that I used. Okay, whenever you cannot meet the set point, if your value go away from the set point, there must be some corrective action to make sure it brings it back to the set point. Okay, so in this case, what is the corrective action? The corrective action is to start to reduce the speed at the VSD. Okay, reduce the VSD, using the VSD to reduce the speed of the pump. Okay, so you will start to ramp down the speed of the pump, your pump will start to move slower, your flow rate will decrease. Okay, now your flow rate will decrease. So this is the third cause of action. VSD will reduce secondary pump speed. Okay, and when that happens, your flow rate will reduce and your DP will also start to drop and maybe will drop back to the set point. Okay, so this is one example of a control loop, a closed loop. Okay, let's say we look one step further. What happens if, let's say I reduce the speed to very, very low speed already, maybe at the minimum speed at 30 Hertz, but the flow, as in the DP, right, is still very high, it's still above the set point. Okay, the differential pressure is still somewhere away from the set point. So what is the second cause of action? Okay, so the second cause of action is the bypass valve will start to open. So you imagine usually over here, right, okay, there will be a bypass valve. Okay, usually at between the supply line and return line, there will be a valve. Okay, we call it a bypass valve. So if the DP is still very high, this valve will start to open. So imagine you supply the cold water, right, before it can flow to all the AHU, it will flow back to the return line first and back to the chiller. So it's like short circuit like that. Okay, you short circuit the chilled water flow. Okay, so you can imagine what will happen. First thing, your DP will drop. Okay, because there's less resistance now between your supply and return, your DP will drop. The second thing that will happen is your return temperature will start to reduce. Because you are supplying very cold water here, 7 degrees Celsius, without even passing through any load, you straight away flow back. So your return temperature will be also will be reduced significantly. Okay, so that's the thing that will happen. That's why over here it says DP and chilled water return temperature will reduce. Okay, what if after you open the bypass valve to 100%, okay, you still cannot meet your DP. Okay, your differential pressure is still high. The third cause of action, the third thing that may happen is this chiller, okay, if 2 chillers is running, it will go and switch off 1 chiller. Okay, so 1 chiller and 1 pump may be switched off because of that. Okay, 1 chiller and pump will be switched off. If there's only 1 chiller running, right, and your DP is super high, then most probably you are oversizing your chiller already. Okay, that means your chiller is not operating efficiently at all. Okay, it's much oversized. Either your pump is very oversized, or the whole chiller plant is oversized. Okay, and you should actually switch off all the chillers and think of way to supply the chilled water, okay, to the individual AHU. Okay, so these are some examples that you can find in the chilled water side, the chiller plant itself. What are the type of controls that is actually present? And how about the condenser water loop? Okay, we know that there's just now what we are talking about is chilled water loop. How about the condenser water side? What kind of controls are there? So remember, let's say you have a chiller. Okay, let's say you have a chiller. And for condenser water loop, okay, so usually there will be a pump. Okay, there will be a pump. And the water will be supplied to the cooling tower. Okay, cooling tower. So let's say you have 3 cooling towers. Okay, so what will happen? There is one parameters that we can actually modulate. So let's say the water go up from here, come back from here. So this is your condenser water supply. This is your condenser water return. So usually you will have a temperature sensor over here. Okay, and a temperature sensor over here. So how do we determine, okay, what is the speed of your cooling tower? Okay, that means if all the cooling tower is attached with a VSD, okay, if they are attached with VSD, how should you control the fan speed of the cooling tower? So one way to control the cooling tower fan speed is to check the condenser water supply temperature. That means this value over here. Okay, so let's say you have a set point, you have a fixed set point. So let's say your set point is 28 degrees Celsius. Okay, this is your set point. And the current temperature, condenser water supply temperature is, let's say, 29. Okay, so let's say it's currently at 29 degrees Celsius. So what happened? You will have to make your cooling tower work very hard, work a bit harder to bring the temperature from 29 all the way to 28, which is your set point. Okay, so that is one kind of control you can have. Okay, so whenever it's above the set point, your cooling tower will work very hard. And when it reaches the set point, then your cooling tower will stay at that particular speed. So that is the first, this one. Okay, condenser water supply will increase above the set point. Okay, so VSD must increase the cooling tower fan speed in order to meet the set point. But that may not be the best kind of control we can have. There's a second way to determine. Instead of having a fixed set point like that, okay, this set point should be, depends on the wet bulb temperature. Okay, it should depends on the wet bulb temperature. So what do you mean by the wet bulb temperature? So let's say you actually install a temperature sensor that measures the wet bulb temperature of the atmosphere, okay, of the ambient air. So let's say your wet bulb temperature over here, is, let's say, 27 degrees Celsius. Okay, so how do you control the cooling tower? Okay, it will depend on the difference between the supply temperature and the wet bulb temperature. So right now, let's say the difference is 2 degrees Celsius. So that means, right, it also tells you that there's 2 degree potential that you can actually reduce. So you can actually reduce your cooling tower, reduce your condenser water supply temperature all the way to 27. Okay, there's this potential to reach this temperature. So you should make your cooling tower work very hard, okay, until it reach the wet bulb temperature. Okay, but sometimes it's not possible, and we use this thing called the approach temperature. So what is approach temperature? Approach temperature is the difference in the condenser water supply and the wet bulb temperature. The difference between these two readings. So in this case, the difference in the reading is 2 degrees Celsius. Okay, your approach temperature is 2 degrees Celsius. So let's say you have a set point. Your set point is approach temperature must be at least 1 degree Celsius. So let's say your set point is approach temperature 1 degree Celsius. Okay, so what happened? You will have to make sure your cooling tower work very hard until you can make your condenser water supply to 28 degrees Celsius. Okay, that means there's a difference of 1 degree Celsius. Then you sort of meet what you want. Okay, meet your desired temperature. Okay, so it depends. Wet bulb temperature may change with the weather. So during a rainy day, this wet bulb temperature may increase to 29. Then, if your condenser water supply is 30 degrees Celsius, it's also okay. Okay, so that's maybe a better way of controlling, because we know that condenser water supply is being affected by the atmosphere wet bulb temperature. So what is the advantages of using condenser water supply only? The control is more straightforward, okay, and the response is faster. Okay, straight away you compare the value and you will control the cooling tower. But the bad thing is it may not be able to reach the desired set point at all, because let's say the wet bulb is 29, no matter how hard your cooling tower is working, it will never be able to reach 28, right? So set point should always be dynamic, it should change accordingly. So using approach is better, okay, because it takes ambient condition into consideration. Okay. Secondly, it is able to supply lower condenser water supply temperature on a cool dry day. That means let's say the wet bulb is very low, like 25. it will make sure your cooling tower, it will make sure your condenser water supply is also can be much lower rather than a fixed point, fixed temperature. Okay, and your cooling tower efficiency will be more obvious. Okay, let's say your approach is very far off every time. Okay, your approach temperature is always you're always not able to reach your approach. That means there's something wrong with your cooling tower. But of course, there's some disadvantages, such as you have higher degree of error. Okay, because now you have additional sensor. And secondly, your wet bulb temperature must be located at a correct place. Okay, if you locate at a very, very humid place, then your wet bulb temperature is not correct also.